Hi ladies and gentlemen, in the last video you have seen how a mode 5 or any counter of any modulus is made by making use of the resetting terminal of the flip-flops. And now then you understood the need for latching the reset signal, and you saw the simulations. Now, apart from using discrete ICs, let us see how I can implement it on a breadboard or a PCB with counter ICs or with discrete flip-flops. So let me start with that presentation. In this the video is organized into your learning outcomes, then a 3-bit up counter using a flip-flop, that is with the negative edge triggered flip-flop 74LS73, and a decade counter using 7490. 7490 is a mode 10 counter, that's a decade counter. Then how I can use it as a mode 8 counter, then how I use 7493, that's a mode 16 counter, and finally the summary of understanding. So this session is for your lab classes, so you can go to the labs, take these ICs, connect them, and appreciate the working. So here you will learn to implement a 3-bit ripple up counter using 7473 flip-flops. 7473 flip-flops are negative edge triggered flip-flops. So each IC contains 2 flip-flops. You will learn to set up decade counter, mode 5 counter, etc. with 7490. Then you will familiarize IC 7493. That's a mode 16 counter. Now I can connect these flip-flops. I can take a 7473 and I can connect this to make a 3-bit up counter. This figure looks like this. So you can apply a 1 hertz clock at the clock terminal, and you can observe the counting sequence from 000 to 111 in the lab. So you can connect these lines Q2, Q1 and Q0 to a storage oscilloscope, and you can observe these waveforms, and you can measure the effect of the propagation delay of flip-flops, frequency division and everything. Now the circuit looks like this. Here this is 17473. This contains 2 JK flip-flops and master slave flip-flops actually, and this contains other 2 flip-flops. So if I connect these 2 together, I can make a 4-bit counter, a mode 16 counter. So but here I am talking about a 3-bit counter only. The last flip-flop is not used, that's all. So if you use the last flip-flop also, you will get a mode 16 counter. So what I do is, this is my first flip-flop. I apply my clock input. This I can connect to an AF generator and apply a 1 hertz clock, a TTL clock, and this is connected to the clock, and this its output. This is my, it's a J and K inputs are here. They are connected to logic high. All JK are connected to logic high because I need a T flip-flop operation, and its output Q. Here, these are negative edge triggered flip-flops. I want an up counting sequence. So what I do is I connect Q to the next clock. These are not leading edge triggered. These are trailing edge triggered clock. Here this is my output Q1. Okay, this is my Q1 output. This is connected to the next clock. You can see that this is the next flip-flop and this is the next clock. Here at this Q output I connect normally on LED, and here I connect to the next clock, and this output you can see that this is my Q2. All J, K are connected to high, and this output Q2 that is connected to an LED. At the same time this is connected to the next clock. So here you can see that it's J and K are connected to 1. Its output Q, this is not this is connected to the LED alone because I am using a 3-bit counter. If you want a 4-bit counter, what you have to do is you connect this Q2 Q output, this 12th pin to the next clock 5. Okay, then I can apply a 1 hertz clock here, and you can connect this counting these are normally when the output goes low, this LED glows. Okay, so you can observe the counting sequence from 000 to 111. Okay, also you can connect this to the storage oscilloscope, and you can appreciate those waveforms. In the storage oscilloscope, you can export those waveforms to CSV file or something, and you can take it out and open with MATLAB or Python, and you can analyze them very subtly. You can. So these are with flip-flops. Now there are some dedicated counter ICs. Some MSI chips are there as counter ICs. So we will familiarize some of them. That is one popular such counter is a 7490 IC. That's a decade counter or mode 10 counter that is internally configured as a combination of a flip-flop, that is a mode 2 counter, and a mode 5 counter. It is a mode 10 counter. It is configured internally as a mode 2 counter and a mode 5 counter. Okay, so that you can connect externally and make it either a mode 10 counter or as mode 2 or mode 5 counter. So it has got two master reset pins, MR1 and MR2, which is internally form inputs to two input NAND gate. So when both MR1 and you can see this diagram here. This is the master reset signals here, MR1, MR2. Here these MS1, MS2. These are connected to two input NAND gate. So when both these are high, when MR1 and MR2 is high, these flip flops are cleared. Or else, if it is normal or for normal operation, you have to ground this terminal and this terminal. So here there are two preset terminals, MS1 and MS2, connected to the function in a similar manner. These are MS1 and MS2. For normal operation, both this reset and this preset should be connected to low. If they are made high, then it will reset or preset, whichever be the case. So here you can see that one is a mode 2 counter, this is a flip-flop, and this is a mode 5 counter. Suppose you want to use it as a mode 10 counter, what I have to do is this output of this one is Q0. Okay, this should be connected to the next clock. This is the clock input. Okay, this I can connect to an AF signal generator, and I can apply a 1 Hertz TTL clock and observe this operation. So you connect this on board, you connect the supply, ground and everything, and then you connect a clock here. This is a clock to this flip-flop, and its output is Q0. This Q0 should be connected to the next clock. Okay, here you can see that next clock comes here. Okay, this is a CP1. This is a clock for the mode 5 counter. So if the first flip-flop output Q0 should be connected to the CP1, that is a clock to this mode 5. Actually it goes to the first flip-flop in the mode 5 counter. So these outputs are Q2, Q3, Q4, etc. You can connect LEDs here and observe this working. So here I am using it as a mode 10 counter. So on powering, the LEDs will indicate the counting sequence from 000 to 1001. Okay, now the same counter I can use as a mode 8 counter. So what you have to do is configure it as a mode 10 counter and reset when this counts 1000. Okay, so it will only count from 0002 to 111. Okay, so what I can do is I can connect this Q3 when this bit, when it tends to 100, the counter should be reset. So what I can do is this is my Q3 output. So this Q3 should be connected to the reset terminal. So this is my Q3. This is connected to my reset terminal here, MR1 and MR2. Instead of keeping it at ground, what you can do is I can keep it connected here. So for all count from 0000 to 0111, this reset terminal is kept at low and normal counting happens. When it tends to 100, what will happen is this reset signal is activated. Both these input to these NAND become high, and this flip-flop, all flip-flops are cleared. So you get a counting from 000 to 0111. After that it counts 0000. In the lab you can verify this operation. Then you can make a mode 4 counter also. Like if this bit is connected to the MR1, MR2, then it will be a mode 4 counter. Okay, so think about how you can make a you can operate as a mode 5 counter. Okay, you can make it as a mode 8 counter. You can cascade a mode 8 and mode 4 to make it a mode 32 counter that way. And there's another IC 7493. It's a mode 16 counter. There's four flip flops are there inside that. So the pin, what you can do is the pin Q0 is connected to CP1. So it's organized as a mode 2 and mode 8 counter. So first is a flip flop and the next is a mode 8 counter. So the flip flop output Q0 should be connected to the clock of the mode 8 counter for mode 16 operation. So you can see this operation. This is 7493 IC. This is my output of my first flip-flop. This is a clock input going here. This is a clock to the mode 2 counter or the flip-flop. Okay, this I connect to an AF signal generator and apply a 1 Hertz clock. So this CP0, this output of this flip-flop is Q0. What I can do is, if I am looking for a mode 16 operation, so I connect this to the clock of the mode 8 counter here. So the remaining is a mode 8 counter. So other things you can connect this way, and you can power up the circuit and observe, apply a 1 Hertz clock here and observe this counting pattern from 000 to 1111. Okay. So you can observe these waveforms in the CRO as well. You use a storage oscilloscope, store these waveforms and analyze them with a computer. You can from the 7492 also, okay, in the lab. That's a mode 12 counter. Okay, so that has a different counting sequence. It doesn't count straight from 000 to 1100. Instead, it has a different counting sequence. You can refer the manual, or you can refer the sheet, the data sheet of 7492 and observe that operation. Now what you learned in this video is that you learned to implement a 3-bit ripple up counter using 7473 flip-flops. They are JK master slave flip-flops. You configure them as T flip-flops and observe the operation. Then you learn to set up a decade counter, mode 5 counter, etc. using 7490. Okay, mode 8 counter actually, I was saying not mode 5 counter, mode 8 counter. Then you familiarized IC 7493 and show the wiring diagram. And that is the end of this presentation. I thank you all.